Okay, welcome to another episode of Circuits from Scratch and Beyond. Today we're going to take care of another Scratch. Okay, but first we're going to take care of this previous episode's mistake that I made, and I'm going to address that, and I'm going to expand on that. All right. So first, let's catch the mistake. I'm going to switch to my laptop view. And let's see if we can catch that mistake. So this is the previous episode snapshot from the previous episode. All right, let's play that and see what if we can catch the mistake. Bigger the voltage, the bigger current. Because okay, here it is. Can you see where the mistake is? I said that the current is going to go up, but I drew the arrow down. Okay, so let's just quickly switch to my PowerPoint, bring it up, and take care of this mistake here. All right, so this arrow here actually should be pointing up. All right, when the voltage goes up, the current goes up. Current and voltage are directly proportional to each other. Okay? Now, just a little visual here. Now let's say we have a power supply. This is the positive, this is the negative side of that. And we have a wire going on, and we're going towards the resistor. The symbol for the resistor is as such. Right? We are going to call that R1. Okay. Our resistor R1 right here. Let me just say right. R1 equals, let's choose some kind of a realistic value here. So we're going to call that 330 ohms. Always write the units beside the number, because as I always say to my students, a number without a unit is just a number. It means nothing, right? So now, what is the voltage that we have? Let's say voltage, some realistic number here. We're going to say V equals 5 volts, okay? Now, through this circuit, if the circuit is complete, which means it will go from the positive all the way to the whatever device we have. In this case, it's a resistor, through that resistor, and it's going to continue and going to end up back into the power supply, but the other terminal. So that means that this circuit is complete. If we break that circuit, that is going to be an open circuit. We can put a switch here if we want. And if we close that switch, we're going to complete the circuit. So let's close this switch and see what values we should get. So we just close that switch here. So now we're going to have a current going this way, and the current is symbolized with the letter I. So what is the current? We don't know what the current is. We know the value of the resistor, which is 330 ohms, and we know the value of the power supply, which is 5 volts. Let's calculate the current. Now, if you noticed, I drew the arrow up this way, that the current flows from the positive to the negative. If you remember my previous lesson, we looked at the electrons, which are right here on the negative side, and they're going to flow, actually they're going to flow from the negative to the positive. That is called the electron flow. But for the purpose of calculating, usually what we assume the conventional current flow. The conventional current flow is that all the calculations are done based on the assumption that the current flows from positive to negative. That's called the conventional current flow. In reality, the electron flow goes from negative to positive. Now, it doesn't matter which way you calculate as long as you stick to the same convention. So if you assume the conventional current flow, make your calculations, all your calculations, according to conventional current flow. That's for the later episodes. But if you assume the electron flow, do all your calculations based on electrons. So just assume one way and stick to it. Right? So we're going to go with the conventional current flow. So let's see what the current is that flows through R1, which is going to be whole current flowing through the whole circuit because there's no any other pathways. Right? So we don't know what the current is. I equals question mark. We don't know what that is. Now, the relationship between voltage and the current and the resistance is as such. I, current, equals voltage over resistance. Now, let's plug in some numbers here, shall we? All right. What is the voltage that we have? Voltage is 5 volts over 330 ohms. Let's plug in some numbers. That equals, and I'm going to call out a calculator on my laptop. All right, let's discard here. Now I'm just going to call up a calculator. Can we see the calculator? Yes. So we're just going to go 5 volts over 330 ohms. Let's plug in the numbers in the calculator. 5 divided by 330. What do we get? We get something that's 0.0151511515. So, yeah. So that's 0.01515, and so on. It just goes on. We can write it like that. Oh, okay, the units are going to be amps. All right, so that's our units. Now let's get this number looking a little bit nicer. So we can multiply this by 1,000, but if we multiply it by 1,000, the amps are going to become milliamps. I'm going to have a separate lesson on that. So let's just not get into the details like that for now. So that whole thing equals 1, 2, 3. So we're going to move the dot 1, 2, 3 times. So we're going to end up with 15.15 milliamps. That's why it's important to get the units. So the current, we can just round it off to, let's say, 15 amps. So the I current, in this case, equals to 15 milliamps. All right, let's confirm this thing with something that's called a multisim. I'm going to call up multisim on the laptop here. I already have this. So what we have here, we have a resistor that is 330 ohms, one of them. We have the power supply, that's 5 volts. Let's just make those connections. And we're going to do it through a switch. So make the connection here. All right, make another connection here, going through the resistor. From the resistor back to the power supply. And in multisim, you always have to connect the ground. If you don't connect the ground, you're going to end up with errors. That's just the way multisim works. Okay, so let's what happens if we press the run button. That means we are starting to run the simulation. So we press that, we close the switch, and well, I guess you're going to have to trust me that the current flows there. But let's plug in some other devices. I'm going to grab a voltmeter or multimeter right here and bring it onto our screen. And we're going to connect the voltmeter across the resistor. Okay, so now we have the voltmeter connected. By double-clicking, I'm going to call up the readout of the multimeter. I'm just going to bring it up here for the clarity. Now, let's set up the multimeter. It's a DC current. We are dealing with the DC current, DC voltage, and we are using this multimeter as a voltmeter. So by default, this is the way it's set up. So let's just leave it that way. And let's close the switch again. But first, we're going to start the simulation. So press the play button. Now, immediately the voltmeter shows 16.5 microvolts. Microvolts, that's 16.5 divided by a million. So basically this multimeter is showing the noise voltage across the resistor. Let's close the switch. What do we have? Oh, we have 5 volts across the resistor. Of course, we're going to have 5 volts across the resistor because this side of the resistor is directly connected to one side of the power supply, and the other side of the multimeter is connected directly to the other side of the power supply. So there is nothing else that we can get. It's just by whatever is on the power supply. And in our case, it's 5 volts. Open the switch again, and we're going to get some really small number. All right. So we have learned something now. Let's plug in an amp meter. An amp meter is a device that measures current across the circuit. So stop the simulation, get another multimeter, and we're going to place it right here. And we're going to make a connection. Goes from one side of the amp meter, other side of the amp meter, and we're going to break the circuit here. So the current flows from the positive through the switch, through the amp meter, and it's just going to go back right into the power supply. That's the conventional current flow. Now let's call up the readout from the multimeter. Double click on that multimeter and bring it right here. So this readout belongs to this, and this readout belongs to this meter. Now let's set up this device as an amp meter. So here, DC, yeah, we're going to leave it as this, and we're going to switch this to amp meter. So now this is going to measure the current. Now let's close the switch and see what happens. Start the simulation, close the switch. What do we have? 5 volts across the resistor. The resistor is 330 ohms. And what do we have on the readout of the amp meter? Oh, wow, look at this. We have 15.151, so 15 milliamps. What did we calculate? We calculated this as 15.15 milliamps. Flies flying. All right, fruit flies. Now, what's happening here? We have just confirmed this on the Multisim. So our calculation checks out on the Multisim. Now let's just do something else on the Multisim. Stop the simulation. We're going to disconnect this part, and we're going to disconnect that part, and we're going to plug in another resistor right here. Okay. Just for the clarity purposes, we're going to disconnect that line right here, switch the ground, put the ground symbol somewhere else, and we're going to connect those 2 resistors in series. And that goes back to the power supply. So now what's the current flow? It goes from the positive of the power supply through the switch, through the amp meter, through both of the 2 resistors, and it's going to end up back in the power supply. I'm just going to extend that line a little bit. Now that multimeter, the voltmeter, we're still going to plug in across the 2 resistors because our total resistance is going to be 330 ohms times 2, which is going to be 660 ohms. Let's see what the current is going to be. So we'll double the resistance. We doubled the resistance right here. Of course, if we get the resistance that is more, it's going to pose more opposition to the current flow. So what should the current be? Well, the current should be less. We make the resistance go up, so we're going to have the current slow down. So the current should be less. Well, let's see. Switch it to the laptop again. And we can start the simulation. I'm going to open the switch, start the simulation, and let's close the switch, make the current flow. Oh, so at 660 ohms, because if you put the resistances in series configuration, they add. Okay? So now, what do we have here? we have two resistances. Let's just, oh, yeah, this is better. Yeah. We're going to have two resistors. Resistor 1 and resistor 2. Right, here's the switch. R1, R2. R1 and R2. So that is this resistor here is 330 ohms. And this resistor right here is also 330 ohms. Let's put them in square brackets right here. We can still see that. That's good. All right, so what's the total resistance of this whole circuit? The total resistance R total equals R1 plus R2 equals 600. Oh, let's just go through the steps here. Which is 330 plus 330, and that is going to end up as 660 ohms. Okay. Let me see it. Sure, we can see it still. Now let's see what the current should be. The current should be, we still have the relationship between the voltage, current, and resistance here. I, current, equals V over R equals V, we still have voltage, we still have 5 volts, over 660 ohms, which equals to, let's call up the calculator on the laptop, 5 volts divided by 660, and that gives us 0.0075 multiplied by 1,000. 1, 2, 3. That's going to give us 7.57, so 7.6 milliamps. Well, what do we have here on this multimeter? 7.6 milliamps. So we can just write this thing down here. So in this case now, the current I equals to 1, 2, 3, 7.6 milliamps. Okay. So now what we have done, we have made the resistance bigger and the current started slowing down. So at 330 ohms with the circuit, the current is equal to 15 milliamps. And at the 660 ohms, when the resistance is bigger, then the current is slowing down, which is smaller value. And it's basically going to be about half of that because we just doubled the resistance. Let's confirm this thing in reality. Instead of the multisim, what I have here is a power supply. Here's our power supply. Here are our resistors. Here's our multimeter. 330 ohm resistor looks like this. We're also going to have a separate lesson on how to read the values of the resistance based on the striped colors. But let's not get into that now. We're going to have a separate lesson. So let's just make some connections. Now, I can see that this power supply shows 5.3 volts. Well, you have to know the equipment in reality, because what I'm going to show you something here. I have set up this multimeter as a voltmeter, DC voltmeter, and I have set the dial to up to 20 volts. We're measuring 5 volts. So if we switch that to 2 volts, it's not going to be enough for us to measure the 5 volts. So we have to switch to the next available range. And this is up to 20 volts. So 5 volts falls within the 20 volts. So that's fine. All right. So now just I'm going to connect the multimeter straight into the power supply just to measure the voltage. And what does it show here? It shows 5 volts right here. And this readout on the power supply shows 5.3 volts. So don't always believe the readout. I'm going to believe the multimeter more than I'm going to believe that little voltmeter that is embedded into the power supply. Always know Always know your equipment, what you're dealing with. All right, let's just keep going here. Over here, we have two sets of resistors. One of them is the 330 ohm resistor. And over here, we have two of them in series. So let's just measure the first one. I'm going to switch this multimeter and I'm going to make it an amp meter. So we're going to have DC amps and up to 20 milliamps. So that should give us enough. The range is up to 20 milliamps. And we're going to connect, what we're going to connect. We're going to go from the power supply, which is this terminal here, and we're going to connect that terminal into the resistor. Then we're going to get the current flowing through this amp meter. So this is the lead from this multimeter here. We're going to make that enter the multimeter, which is the amp meter. And from that, we're going to connect that straight back to the power supply. So that is going to be our circuit. Let's see what we have. At 330 ohms, oh, well, it's not showing anything because we haven't set up multimeter yet. This terminal shows volts and ohms. And this terminal, if you want to, we should use this terminal if we want to measure the current. So we're going to plug it in here. Now we should have the circuit complete and see what the circuit shows us. All right, so at 330 ohms, at 5 volts, because we have set it up to 5 volts, it shows 5.3, but it really is 5 volts in this power supply. Going through the current is flowing through the resistor, through the ohm meter, and we get 15 milliamps because the range is up to 20 milliamps. So whatever we see here is going to be in milliamps. So that's 15 milliamps. Now let's connect this thing to two of those. It should be half of that. So two of the resistors, 660 ohms. And that is going to give us about half of that. So we have confirmed this number or this current flow and the values. We have confirmed these in our calculations on the board. We have connected that same circuit in a software that's called Multisim that checks out also. And we actually, what we did is we have connected the circuit in reality and we have connected the real equipment and we have confirmed that in 3 ways: calculation, Multisim, the software, and we have connected the circuit. So now you know the relationship between the resistance and the current. So right now, you should know that if the resistance goes up, the current is going to go down, and vice versa. If the resistance goes down, of course, there's going to be less resistance. Here, let's make a proper arrow here. Then the current is going to go up. We call that, in a circuit, the resistance and the current, they are inversely proportional. If they were directly proportional, they would match the directions. Okay, so we have taken care of the answer of what the mistake was in the previous episode, and now you know the relationship between the resistance and current in a simple series circuit. Okay, my name is waltbak. For the circuits from Scratch and beyond, stay tuned for more. Bye.